organized by IIT MA. And for this session, we have Professor Ramakrishna P A, who will be talking on access to space, can cost be reduced below the SpaceX level, and other alternate ideas. This evening, we have the honor of learning from an eminent scholar, scientist, and most of all, a person deeply committed to expanding our understanding of the universe. Professor Ramakrishna P A completed his bachelor's in engineering from National Institute of Engineering, Mysore in 1993, and in 2003 he completed his master's and PhD at IISc Bangalore. In 2005 he joined IIT Madras as faculty and is currently a professor in aerospace engineering at IITM. He has spent the last decade understanding solid propellant combustion and developing systems with extending range of ramjets with the use of highly dense fuel-rich solid propellants. He has taught various courses for graduate and undergraduates primarily on combustion and propulsion. He has over 50 peer-reviewed international journal publications and 60 conference publications. And he has guided around 10 doctoral theses and 10 master's theses. I humbly welcome Professor Ramakrishna P A. And once again, I welcome all of you to the event. Over to you, Professor.
Thank you very much. At the outset, I would like to thank the IITM Alumni Association for giving me this opportunity to present some of my thoughts on this topic. Thank you very much. And please, can you put on the slideshow? Yeah. Please don't get confused with the title. There were two titles that somehow came up. One was space transportation, where are we and where are others? There was also one more title that I put up, which was what was announced, but it doesn't matter. The matter remains the same. Next slide, please. Next. If we look at the world map and look at which are the countries that have a capability to launch vehicles or satellites into space, there are very few countries in the world that can do that. And this shows who are all the countries. If you look at countries alone, it is US, Russia, China, India, and Japan. Europeans combined together, many countries combined together, and under the umbrella of ESA or European Space Agencies, they launch their vehicles. So there are very, very few countries that can do this launching of satellites on their own. So next slide, please. So let's firstly look at US. US earlier had NASA, which was pioneering their launch vehicle program through the space shuttle. Now, after they decommissioned the space shuttle, they have only 3 private companies, Orbital ATK, United Launch Alliance, and SpaceX, which are launching their vehicles. So we look at what are their capabilities a little later. Next slide, please. Yeah. Orbital ATK has the Antares vehicle, which is a very large vehicle. I'll try and compare what is the payload that can be taken to LEO. It is there at the bottom. LEO stands for low Earth orbit, right? So the payload capability to LEO is the common factor that I have. And the launch mass is what I would be looking at. So if you have a very large launch mass and a very small payload, it's a bad design. If you have a reasonably large payload and a smaller launch mass, it's a very good design. So that's where that's what you need to watch out for. So this has somewhere around close to 300 tons of launch mass, and it can take something like 7 tons to low Earth orbit. Next slide, please. Now, the ULA has three launch vehicles. One is the Atlas, Delta, and Delta 2. Now, Delta 4 is a very, very large vehicle with a launch mass of around 733 tons. And you can see that it can launch something like 28 tons to low Earth orbit. It's a huge vehicle. Next slide, please. One way people do increase the increase the payload to low Earth orbit or any other orbit is by adding many strap-ons or many more stages. So the last one that we have in the US launch vehicles is the SpaceX Falcon 9. Now, this is a two-stage vehicle, and it can launch something like 22 tons to low Earth orbit, and the launch mass is around 550 tons. Now, SpaceX has been in a lot of news. We'll cover that a little more as we go along in this presentation, and how can we compare ourselves to SpaceX, and what are the things that we need to do in order to match them or better them. Next slide. Now, the Russians have been having their Soyuz and Proton programs. Soyuz is their smaller vehicle with something like 305 tons launch mass, whereas Proton is a very large vehicle with something like 22 tons to low Earth orbit. Soyuz, in fact, has had probably more than 2,000 launches till date, and the European Space Agency seems to use that also as one of their launch vehicles. Next slide, please. As I said, European Space Agency, you have Arianespace, wherein you have three vehicles. Arianespace has also Soyuz, which is taken from Russia. And you have Ariane 5, or as the French would call it, Ariane 5, which is a launch mass of around 800 tons, and its capability of launching payload to low Earth orbit is somewhere around 20 tons. Whereas Vega, which is based on solid propellants, is a much smaller vehicle, which can launch something like 2.5 tons to low Earth orbit. Next slide. The Japanese have a two-stage vehicle, H2B, which is around 530 tons and can launch something like 19 tons to low Earth orbit. Most of these launch vehicles either use liquid oxygen and liquid hydrogen as their propellants, or they tend to use liquid oxygen and kerosene. More recently, of course, they are going in for something known as methane, liquid methane, as one of the fuels other than liquid hydrogen. Next slide, please. And of course, the Chinese have their Long March series, and the biggest of them is Long March 5, which can launch something like 23 tons to low Earth orbit. So the Chinese have also a proven capability to launch both small and large payload to low Earth orbit. Next slide, please. And ISRO in India has been pioneering our launch vehicle program. And if you look at the three standard vehicles that are there with ISRO, one is PSLV, the Polar Satellite Launch Vehicle, and GSLV Mark II and Mark III. GSLV Mark III is one of the biggest vehicles that has been built in India. And if you look at the payload capability here, it is something like 640 tons is the launch mass, and it can launch something like 10 tons to low Earth orbit. And it's a 3-stage vehicle or a 2.5-stage vehicle with 2 solid strap-ons and a Earth storable bipropellant core. And the last stage is LOX hydrogen engine. So this is the configuration that we have, whereas PSLV is more of a mixture of all these things that we tried out initially, which is solid strap-ons plus solid core, then Earth storable bipropellant first stage, second stage, and then again a solid, and then a bipropellant liquid as the final stage. So it's a 4-stage vehicle, whereas GSLV Mark III is a 3-stage vehicle. One thing that we need to notice as we go forward, people are looking at reducing the number of stages. Although one would argue that, if you have more stages, your payload capability will increase because you are expanding out some things that you are not using. But however, one needs to remember that when we are trying to expand out what we do not require, it also lowers our reliability, because things could go wrong when you have a stage separation. And therefore, in order to improve on the reliability, which is still very poor as an industry when compared to other industries, because the launch vehicle industry is somewhere around 98.5% reliable, which means that 1.5% of the launches are not very successful. So in order to improve the reliability, people are going towards more of, lesser number of stages and reducing the number of stages so as to make sure that the reliability of the vehicle goes up. Next slide, please. So now comes this question of who's more economical. We've seen the comparison of what is the mass that we are going to carry to low Earth orbit, and we need to add to this the cost factor. So when we add to this the cost factor, and we look at some of the vehicles that have a smaller payload capability, I will tell you why I have done this differentiation. Sometimes the large vehicles have an advantage because they can have a better payload capability, and therefore their launch costs will also come down. However, if we are to look at what is the kind of payload that it is going to launch, if you have, let's say, 20 tons to low Earth orbit, you need to find so many satellites to go on board if you have to launch that, which itself will require a long time. So there are 2 sets of vehicles that I've tried to compare. One is a smaller vehicle, which is PSLV class, which is up to something like 10,000 tons to low Earth orbit, as you can see here. Can you move this? At the bottom, there is this thing that allows you. Yeah, thank you. I'll leave it like this. This is, I think, better than the other one, because some of those things were not visible at all. So if you look at PSLV, and if you do the comparison of how many US dollars does it take to launch 1 kg of payload in PSLV, it comes to something like 4,600, which is the lowest in its class. So it goes to say that ISRO has kind of put in a lot of things wherein it is trying to make the costs also lower. We need not be, if you look at the payload capability, we are probably not the highest in the class, but that doesn't matter. What matters is how much does it cost to that kind of pay. Next slide, please. Now we look at the next this thing wherein it is a much bigger vehicle, right? It is beyond 10,000 kgs to low Earth orbit, all the way going up to 22 tons, which is Falcon 9. Now here the comparison uh, is really very interesting, because Falcon 9, which is something that SpaceX is building, is somewhere around $2,700 per kg, which is much lower than what was there earlier, the PSLV, which was 4,600, and much lower than anything else that you can see in this table. So it seems that you have a very low cost access to space with Falcon 9. Now, one needs to understand why this is happening, and can we then Falcon 9? Because if you look at GSLV or PSLV, it is not there. PSLV in its class is the lowest, but when you go to large vehicles, Falcon 9 seems to be the lowest low cost access to space. Next slide, please. Here I've tried to compare, or I've tried to put together what causes this Falcon 9 to be the cheapest. One is economics of scale. As I said, if you have a very large vehicle, then your payload capability also improves. You can do a lot of things to make sure that your payload fraction is much higher. When you have smaller vehicles, it just doesn't help, because some things need to be there in that vehicle, and they occupy a certain weight fraction. So the weight fraction of the payload goes up in larger vehicles compared to smaller vehicles. So that is economics of scale. The other thing that has been done very nicely in Falcon 9 and in all the SpaceX program is they have not tried to do what we in ISRO are trying to do. ISRO is trying to have different kinds of propulsion systems, like that is one solid, one earth storable bipropellant, and then a cryogenic engine. Whereas what Falcon 9 has done is it has a single propulsion system and a single engine design. So he'll make many components of the same. So again, economics of scale and repeatability in manufacturing and ease of manufacturing of all these things contribute to the low cost. Then the other big factor that contributes to the lowering of the cost is typically something like 80 to 85% of the any launch vehicle is expendable mass. That is the problem. So if you take a if you take launch mass of around 50 tons or 100 tons, 80 tons would be 80 to 85 tons would be propellant, and typically 3 to 5% will be payload. So when you have so much of expendable material, it would make sense to make sure that the costs of these propellants are lower. If we can ensure that, then we would see that the overall cost can come down, which is what has been done in the Falcon 9 program. They have made use of LOX kerosene engine, and liquid oxygen and kerosene are the propellants that are used. Now, liquid oxygen, it is believed, is somewhere close to 1 liter of milk, which is somewhere around 40 to 50 rupees a kg in India. And kerosene is aviation grade kerosene, which should be somewhere around 100 rupees a liter in the market. So when you have such low costs of propellants, it just helps in bringing down the overall cost. The other aspect that he has looked at is the low structural mass factor. What do I mean by this? There is a certain amount of dead mass that we have to carry in a launch vehicle. That is the structure that is holding the vehicle itself, and many other components like electronics and other things that go on a launch vehicle. If this mass is smaller compared to the overall mass of the vehicle, which has been kept around 3.5 to 5% here, it would also mean that the overall cost would come down. And if you can introduce reusability, which has been done in this case, because the entire structure can be brought back, it makes it even more lower cost because you are reusing the typically in launch vehicles. If you look at most launch vehicles, they are expendable. That is, the structure goes and falls into the ocean, so it is not recoverable, and therefore it is a one-time cost. But we still sometimes need to use very exotic materials in order to make that material live, and we seem to junk it with one-time use, which is something that is increasing the cost. Next slide, please. Now, if we also look at what are the upcoming vehicles that space agencies worldwide are designing, NASA is coming up with a huge vehicle, which is going to take something like 130 tons to low Earth orbit. And its launch mass is somewhere around 2,650 tons. So it's a huge vehicle that they're coming up with, which has two stages. One is a solid stage, and then a liquid oxygen, liquid hydrogen system. Next slide, please. Then SpaceX itself is coming up with a much bigger vehicle, which is essentially, if you're looking at Microsoft, this thing, it is Control-C, Control-V. What he has done is copied the same thing on and made it a bigger vehicle. So the launch mass is somewhere around 1,400 tons, and it can launch something like 63 tons to low Earth orbit. Next slide, please. The other vehicle that, as I said, they're trying to design and come up with for interplanetary transport and other transport. In fact, Elon Musk has been trying to say that he is going to colonize Mars and also use some of these vehicles for intercontinental travel on Earth also. Now, here is where there has been a change in things. He has started to look at methane. Now, there's a distinction between hydrogen and methane. One is something called the specific impulse, which I'll come to a little later. Now, this is a measure of performance. The measure of performance being better with hydrogen because the molecular weights of the product gases will be lower. As you go to hydrocarbons, the molecular weight of the exhaust gases will go up because there is carbon also present in the fuel. And depending on the amount of carbon in the fuel, your molecular weights go up. Incidentally, CH4 happens to be the lowest molecular weight hydrocarbon. And using CH4 will give you very good specific impulse, as I talked about. And in addition, if you look at liquid hydrogen, which needs very low temperatures to store it at, typically it's stored at 20 Kelvin. And even at such low temperatures wherein it's a liquid, its density is around 70 kg per meter, which is very, very low. Now, methane, on the other hand, the storage temperatures are much more higher than hydrogen. And in addition to that, it also has something wherein its density is much higher. It's somewhere around liquid methane has a density of somewhere close to 400 kg per meter cube. So the volume that you need to store the required mass in comes down. So that's a very big advantage in spaceflight. Next slide, please. Then there is Blue Origin, which is also trying to come up with this LOX methane and LOX hydrogen engine. It has a 45-ton payload to low Earth orbit. Next slide, please. Strato launch systems. I think this was there in the news very recently. They rolled out this vehicle. It is a very, very huge vehicle. It is a combination of an aircraft and a rocket. As you can see, it takes off like a traditional aircraft, but the only point being that the wingspan is very, very large, and therefore you would need specially designed runways for this. But however, it takes off like an aircraft, which makes special launch pad requirements being not there. And the rocket that is there at the center is something that is going to be released at around 11 kilometers, wherein the aircraft would be traveling at somewhere close to 0.8 times the speed of sound. So from there, it takes off. So this increases the payload fraction simply because what happens in these cases is if you look at the rocket going to space, a large fraction of the propellant mass is burnt in the lower stages itself. And it makes, out of that fraction, if you take a look at what is the oxygen content, it is substantial. What this does is when it uses air breathing engines to go up to 11 kilometers, it is doing away with all that. And it can go up to 11 kilometers and then release that rocket. So the payload fraction of the vehicle improves significantly. Next slide, please. This is again a similar concept that Virgin Galactic also uses. So here again, they are not trying to take a payload. They are only trying to go with 6 passengers to something like 110 kilometers altitude. And the central vehicle is the one that goes up. And that is based on a hybrid rocket. I'll explain in a minute what a hybrid rocket is. So this is to give passengers a feel for space flight and zero gravity. Next slide, please. And ISRO is also looking at building a new class of vehicles. I've only looked at the larger one that is called as the Unified Launch Vehicle, wherein it is again going to be a 2-stage vehicle, and it is going to have only 2 sets of propulsion system. One is liquid oxygen and kerosene. RP1 stands for rocket propellant 1 or kerosene, and liquid oxygen and hydrogen. So here there's a substantial improvement in payload. It can go all the way to something like 15 tons, which was earlier 10 tons with GSLV Mark III. And its launch mass is somewhere around 700 tons, which is comparable to GSLV Mark III. So what they tend to change, it's a single vehicle. What they tend to change in order to achieve this flexibility in payload is only the strap-ons. If you see here, the strap-ons are bigger or smaller depending on what is the payload. So that's the kind of idea with which ISRO is going ahead. Next slide, please. So this gives you a kind of glimpse of, I've tried to put it together in such a fashion that the size is maintained. The ones on the extreme left are what ISRO is doing, which is not visible because I've tried to shrink it such that the size is something close to what it is compared with the SpaceX. So you can see that there is a small scale and there is a very large scale, SpaceX being the largest. Now, one thing that might be of interest is to look at what's happening on the satellites. Typically, as electronics size is shrinking and electronics weight is shrinking. So I'm personally of the opinion that in India, we don't need to go to very, very large scale vehicles unless we are looking at intercontinental travel and things like that, which I'm not sure how it will pan out in the future. But otherwise, I do not foresee satellites being very large and very bulky. But satellites being small, because electronics size is shrinking, is something that is going to be the order of the day according to. Next slide, please. So this is something that I said is the comparison with other in the field. And let me spend the next few minutes trying to tell you what is it that we in IIT Madras are doing, so that we can look at some things different. One is, other than the Virgin Galactic, there is nobody else who's making use of something known as hybrid rockets. Typically, in a solid rocket, you will have, as you can see here, you will have a solid propellant, which is both fuel and oxidizer put together. But in this one, the fuel and oxidizer are separated. There's a separate oxidizer tank, and there's a separate fuel storage area. And they're only mixed when you need to mix it and burn it. So it burns in this combustion chamber, as I've indicated it here, and is expanded. That is, its pressure reduces and its velocity increases when it goes through a convergent divergent nozzle. Now, there is one parameter that I would want you to pay attention to, which is known as the ISP. Now, ISP is something which is defined as thrust per unit mass flow rate of propellants. That is, what we get as an output is thrust, and what we need to pay for it is something which is the mass flow rate of the propellants. That is, the propellants that are carried on board are expelled out at a certain rate in order to achieve a particular thrust. So this is a measure of performance. And if you look at it, one of the things that is a standout feature of this kind of a system is that its performance is comparable to liquid oxygen and kerosene systems that are currently being thought of and used worldwide in order to reduce the launch costs, as I've said. One other feature, as you might notice, if you are using completely a liquid system, then you need to carry two liquid storage tanks and feed systems and other things, which means a large number of valves. And here, that complexity has been reduced by half with a hybrid. Next slide, please. Here, I've tried to compare what is the ISP, that is, what is the thrust produced per unit mass flow rate of propellants. And if you look at wax alone, which is given by the blue line, the one at the bottom that starts at the bottom, the sky blue line. Now, it has a ISP that is comparable to liquid oxygen and liquid kerosene. Now, notice that its ISP peaks around somewhere around 2.5, whereas when you add aluminum to the fuel, you get it at a much lower oxidizer to fuel ratio. What do I mean by this oxidizer to fuel ratio? If you have more oxidizer, which means it's a liquid and its densities are much lower than compared to solids, so your vehicle will be more voluminous. So it makes sense to reduce the size of that volume by carrying less of the oxygen and more of the fuel. So if you move this O by F to the left and you still are able to retain that performance, that's a very good thing to do. So this kind of a fuel gives us that advantage. Next slide, please. Next slide, please. Thank you. So what we try to do now is to try and construct a launch vehicle based on this kind of a propulsion system, that is liquid oxygen and wax. And if you look at the configuration, it is quite similar to SpaceX, wherein it is repeatable engines. That is, the same engine is repeated many times. So here in this figure, you will see that there is 1, 2, 3, 4 engines of the same kind. And you see that there is a payload capability of something like 450 kgs to low Earth orbit, when the vehicle lift-off mass is around 55 tons. So this is one configuration. Next slide, please. That we've come up with. The other configuration that we've looked at is something like if you have 2 strap-ons, what is the kind of configuration that we will get? The 2 strap-on one is 55 tons that I've shown you. And if you go for 4 strap-ons, you might get a much larger payload to low Earth orbit, which is around 1.1 tons. Next slide, please. And a low Earth orbit is something that is 500 by 500 kilometers at apogee and perigee. Now, using this kind of a vehicle, if you have a liquid oxygen, a liquid hydrogen third stage, as shown here, this portion at the top is something that's new from the previous one. Here, you can go all the way up to 1,800 kgs. And when you compare the costs, we worked out this cost based on certain assumptions that we had to make, and certain knowledge of what is the fuel weight and what is the fuel cost and oxidizer cost. This comes down to something like $3,300 per kg, which is quite good compared to other systems that are in existence, primarily because, one, it makes use of repeatable stages. 2, the propellant's cost is much smaller than any other propellant's cost. Next slide, please. And can you play that video from outside, please? Because it will not play here. We have done this testing at Sriharikota, wherein we've made this rocket, which has a thrust of around 1 ton. And this is the video of that. So this is something that we have done now. Can you go back to the presentation, please? So can you just go back one slide, please? Yeah. So the specific impulse that I talked about is somewhere close to 300 seconds, which is very good compared to what you have in the market. And as I said, it has a 1 ton thrust, which we've been able to build here. Next slide, please. This is my last slide. The way forward, as I see it, is which is something that people are working on, which I've not covered in this talk, because it just becomes too big a talk. One is to use air breathing engines, which I briefly touched upon when I talked about stratoshift, and reusability of launch vehicles. And the biggest thing is to make sure that the structural fraction should be low and a drag should be low. If you have any queries or any things that you need to contact me on, this is my contact details. You can feel free to write to me or call me regarding this at any point. And lastly, my acknowledgements to, next slide, please. My acknowledgements to Dr. Nikunj Rathi, who did his PhD in the same lab, and he is the founder and director of Rathi Aerospace Labs, in making this presentation, and also with my other colleagues and research scholars at the Rockets and Missiles Lab, which is which has led to this presentation. Thank you. I'd be happy to answer any questions that you have.
Okay, sir. So we have a few questions.
Yes, please.
So the first question is, why is that NASA is focusing on low Earth orbit missions but not focusing on getting manned missions? What's the rationale?
Sorry?
Why is that NASA is focusing on low Earth orbit missions but not focusing on getting manned missions? What's the
No, no,
rationale?
no. It's not that NASA is not focusing on that. It's just that for the comparison's sake, I put all of them on the same denominator. I just put it as a comparison with low Earth orbit for everything, so that it is the same. Because there are some vehicles that only go up to low Earth orbit. There are some vehicles that go to a geostationary orbit or interplanetary orbit. Then comparison would be very difficult. So in order to make the comparison uniform or better, I have made all of them low Earth orbit. But it's not that NASA is not concentrating on manned missions or any other such missions in the future. They are working on that large vehicle that I showed you, which it can be used for any such applications.
Okay, sir. We have one more question.
Yes, please.
One person is requesting you for your comments on Aerospike.
Sorry?
A request for comments on Aerospike.
You mean the aerospike nozzle? Aerospike nozzles typically don't find much use in any of the launch vehicles or in this, primarily because the heat transfer to the spike is very, very large, and that has been a stumbling block in designing or developing that. Although the advantages of it have been proven quite early, but the if you have a very long time of operation for the engine, and if you're trying to use the aerospike, although it gives you a very good uh, performance across altitudes, it's just that the heat transfer is something that makes it very difficult to realize for any reasonable application in the past. It doesn't mean that it will not happen in the future.
Okay, sir. We have one more question. Why is ISRO focusing on low payload as compared to other agencies?
Okay. Every space agency has something that is their own requirement. If you look at our own satellites, our largest satellite is somewhere around 6 tons to not to low Earth orbit, but to the GS transfer orbit. Now, if you look at launching that, that can be done with the new unified launch vehicle. It's still not possible with GSLV Mark III, but however, as I said, the electronics weight and the weight of other systems is decreasing with time, and the volume is also shrinking, which makes it look at launching only that class of things that we think is enough for our requirement. So ISRO is currently focused on only Indian requirement, and that is where we are aiming at low size satellites.
Okay, sir. So the next question is, Falcon carries 60 or more satellites at a time. So isn't payload capacity important for cost per satellite?
Yes, it is important. Large payloads will help in reducing the cost, which is what I said. Because Falcon 9 can carry a very large payload, it can bring down the launch cost. But on the flip side, if you are a user, as in if you are somebody with a satellite, what you need to think is Falcon 9 can be launched only with a certain amount of booking. That is, how much of your this is, you can look at it as travel through bus. If you go by buses, sometimes the bus drivers don't leave because it's not completely filled, and they would wait till it gets filled. Here, uh, if you have to do that, you will have to wait till a certain percentage of the payload fraction is completely taken up, which makes the wait for somebody who has booked a satellite to be launched longer. Which is the precise reason why ISRO is trying to build something called a small satellite launch vehicle, which is something that makes use of solid rockets. One of the advantages with solid rockets is you can make them and store them. Something similar to what you do in missiles. You make them and you can store them and use them whenever you need them. So if you have the idea with which ISRO is going ahead is, if you have this small solid rocket vehicle, then you can launch them on command, and they say that within 2 to 3 days of booking, they can be launched. So these are two extremes, and as I said, I would go with the strategy that ISRO is following, simply because the payload sizes are shrinking. But it does change a lot if SpaceX is able to launch people from one continent to other using these rockets in a very small time and at reasonable cost. Then it's a game changer.
Okay, sir. So the next question is, what is the status of development of hypersonic vehicle?
Hypersonic vehicles in India have been uh, developed by both ISRO and DRDO. Both those vehicles have been tested. One of them was tested in early 2016. The other one was tested last year. And worldwide also, there have been tests of hypersonic vehicles. But hypersonic vehicles are more useful on missiles than on launch vehicles. Simply because if you look at launch vehicles, you need to impart a certain velocity to the satellite for it to remain in orbit. Now, if you have to impart that velocity to the satellite, it has to be an accelerating flight and not something wherein it is cruising at a particular velocity. So these kind of hypersonic engines are more useful on missiles rather than on launch vehicles.
Okay, sir. So the next question is the rocket and starter launch system released horizontally or at some angle?
Sorry?
Is the rocket in starter launch system released horizontally or at some angle?
It is released horizontally. It will have to be dropped from the vehicle and then it will ignite. Much similar to what you would find with if you've seen the video of how BrahMos is launched from Sukhoi, or the other one is there a vehicle that the Americans have another rocket that is launched from airplane, which is also very similar. That is, it is dropped, and once there is a difference of certain separation distance, then the engines turn on, because they do not want some failure in one of the engines to come back and hit the mothership.
Okay, sir. So the next question is, though electronics are getting lower, but human weight remains the same.
True, but if you look at the number of human launches to either space stations or to another what is they only launched to the moon. Those number of launches are very, very small. So people tend to go with electronics to be, I mean, the satellites to be launched rather than look at the humans.
Okay, sir. So the next question is IITM doing any work on reusable launch vehicles?
Yes and no. Yes is for wanting to do and having done some small bit, but no is because we've not demonstrated anything that is of that magnitude that can trigger the interest in the market.
Okay, sir. So the next question is, are air-breathing engines only for suborbital launch vehicles? Can you tell about some agencies researching that in INSTI? Researching in that, not in INSTI, sorry.
Can you tell about some?
Agencies researching in that.
Okay. Certainly, air breathing engines are not for only suborbital. As I said, the Stratoship that is one of the air breathing engines going up to Mach number of 0.8, that is 0.8 times the speed of sound, and launching it from 11 kilometers. Now, there are other such concepts being thought of, because that makes the launch cost much lower than the other ones, as I said, because you are carrying more of oxidizer. However, uh, these have not caught on to something that is very large scale. The Chinese have something which they are coming up with, wherein they're trying to use a gas turbine engine, which can go up to Mach 2, that is twice the speed of sound. And from there on, rockets take it further up. So there are strategies that people are looking at in order to make sure that the launch costs are lower. But it's like this. Somebody has to be the set the cat among the pigeons. Currently, Elon Musk has done this successfully with SpaceX, which has meant that everybody looks at what is the cost per unit weight of launch. When I joined IIT Madras, I remember having talked about launch cost being more than $10,000 per kg. We have now come down by almost an order of magnitude. So there are a lot of agencies that are researching. As I said, ISRO is also trying to build a vehicle based on scramjet, which is again an air-breathing engine. But here, this thing is we have to take it up to that particular Mach number where the air-breathing engine is going to start.
Okay, sir. So the next question is, can you give us an update on Gaganyaan mission, the launch vehicles used for that? How is the launch vehicles used for it different from that used to launch satellites?
Okay. Gaganyaan is going to be the same launch vehicle as GSLV Mark 5. It's not going to be anything different from that. Only the features that are going to be added to it is the crew module, as they call it, needs to be, in case of an accident, something similar to what you had with space shuttle. The crew module needs to separate out from the mothership very, very quick. And that's very similar to what you have as pilot ejection mechanism in aircrafts, fighter aircrafts especially, wherein pilots can eject at the last minute when something wrong is there with the aircraft. Very similar to that, they have an ejection mechanism on the launch vehicle, so that the crew can be taken out safely and it can land in the ocean, and that can be collected later on by any ship. So that's the only difference. That crew module is something that is going to be different from the rest of the vehicle.
Okay, sir, that's it. That's all of the questions.
Thank you. Thank you very much for all your questions. I hope I've answered them to the best of my abilities. If you still feel that you need to ask me anything, as I said, feel free to write it. Thank you. Thank you so much for this opportunity.
Thank you so much, sir.
Thank you, sir.